In this class, we will discuss about another problem on torsion of multi-cell section. But here the difference is we are considering an airfoil shape. The airfoil shape means it is something like this. It is not having definite geometrical dimensions with different thicknesses. That is another thing. So one is airfoil shape. Another one is it has got different thickness at different segments. Now this is the given problem. So this is in airfoil shape. We can see here there are some S values. S values, they are nothing but the lengths, center line lengths you can say. So for example here S is equal to 57 centimeter means that is this length. Where that Q1 is flowing. If I take this as cell 1, so Q1 is the shear flow in this. And from here to here, this is S, 67 centimeters as given. And S2, the another S is given here, 33 centimeter. That is from here to here. Web. So this is the interval, that is the middle web portion. Its length is 33 centimeter. Next, another S is given, 60 centimeter. That is from center of this to here. This is from here to here. It is 63. Then 48 centimeter. That is from here to here. From here to here it is 48. And 67, that is from here to here. So you can see there are different values of S here. This S is from here to here. This S is from here to here, 33 centimeter. And this 63 centimeter is from here to here. 48 centimeter is from here to here. 67 is from here to here. So instead of giving center line, that is center to center distances or median distances, he has given the periphery something like this, circumference. Anyway, we need the distance of for the shear flow calculation. And he has given different thicknesses also. You can see here, this has got a thickness of 0.06 centimeter. 0.06 centimeter means 0.6 mm. So anyway, let us retain the dimensions in centimeters only. Next, this thickness is 0.09 centimeter. This thickness is also 0.09 centimeter. This is 0.08 centimeter, and this is 0.09 centimeter. Web portion. And he has given that this airfoil section is subject to a total torque of 10,000 Newton meter. So this is given in the problem. Anyway, there are two different cells here. Cell 1 and cell 2, I have written here, cell 1 and cell 2. So here, this cell 1 and cell 2, both together, they are subjected to 10,000 Newton meter or 10,000 10 power 3 or 10 power 7 Newton millimeter torque. So T1 is the torque in the first cell, T2 is the torque in the second cell. So total torque is T. Now A1, he has given this area. So area of this area within the boundary for the first cell, he has given 680 centimeter square. So distances are on centimeters, thickness is in centimeter, area is in centimeter square. A2 is the area within the boundary of the second cell, that is 2000 centimeter square. Here the question is, determine the internal shear flow. That means Q1, Q2, Q3 we have to find out here. So let me take Q1 as the shear flow in the first cell, like this. Q2 is the shear flow in the second cell. Q3 of course it is in the web. So similar to the earlier problems. So to solve this, I will take the torsion equation first. T is equal to T1 plus T2. So T is 10 power 7. So of course here, okay, I will Newton centimeter is there, you know. So what I will do here is, since the other things are in centimeters, I will convert this also into centimeters. So this becomes 10 power 6 Newton centimeter. So I can write here 10 power 6 instead of 10 power 7. So Newton centimeter. So and if you substitute that, so T1 you know it is 2 Q1 A1, T2 is 2 Q2 A2. That is the formula. So if you substitute the values, so this is 10 power 6 is equal to 2 Q1 into A1 is given as 680, I will write it as it is, into 2 Q2 into A2 is 2000. So if you simplify that, you get this one equation, first equation. So 1360 Q1 plus 4000 Q2 is equal to 10 power 6. This is the first equation obtained from the torsion equation. So Q1, Q2 we have to find out, they are the unknowns. Now the next thing is I will calculate. So here I am doing in a different way because the thicknesses are different. So in this problem, since thicknesses are different, I am going to use a different approach. I am going to calculate the closed integrals for the cell 1 and cell 2 separately. Closed integral means that is integral ds by t. So for the first cell, for this cell, I will calculate closed integral ds by t. I will call it as a1, small a1. So for the first cell, what happens? Including the web. So first cell means this one plus this. So from the given problem, this length is 67 centimeter and its thickness is 0.06. See here, of course this is also 0.06. The thickness of that is 0.06. So this S is 67 divided by 0.06. ds is 67 divided by 0.06. T is 0.06 plus for the web portion, distance is 33, thickness is 0.09. So I have to add, because it is integral, I have to add the ratios of length to thickness. So plus 33 divided by 0.09. If you simplify this term, you are going to get 1483. So what I have done here is I have calculated the closed integral for the first cell, which includes the web also. Next, similarly for the second cell, the closed integral once again including the web. For the second cell, what happens? This is second cell. You have 4 values of S for the second cell. So one is 63, another is 48, another is 67, and including web means 33 also. That divided by the corresponding thickness we have to take and we have to add it. So here, if I do that, so first I will take this web portion, 33 divided by 0.09 plus 63 divided by 0.09. See here. So see here, plus 48 divided by 0.09 plus 67 divided by 0.08. So this is the closed integral value for the second cell, which comes out to be 2409. Now for the web I will calculate separately. I call that as A12 because web is common for both cell 1 and cell 2. I will use the notation A12. So for the web it is only 33 divided by 0.09. So please note that for A1 and A2, including the web, we have to calculate the closed integral ds by t, and for the web separately we have to calculate. Now after calculating those closed integrals, we have to apply the compatibility equations. So in the case of compatibility equation, so in terms of Q1, Q2 and Q1, Q2, A1, A2 and A12, so we have to write these compatibility equations like this. So this, better you remember this because I am not going to detail about the derivation and all. So similar to what we have used in the earlier problem, 2g theta is equal to like that. So there I had expressed in terms of shear stress and S, tau and S and A. Here I am expressing in terms of A1, A2, A12, Q1 and Q2 and A1 and A2. So like that. So if I write the compatibility equation for the first cell, so 2g theta is equal to 1 by A1 into A1 Q1 minus A12 Q2. Please remember that this is for the web. A12 is for the web. Okay, I have to take minus sign here because I am reading that from that Q1, this Q2 is going away. For the second cell, it is in the reverse way. It is very easy to remember. It is in the reverse way. 1 by 2g theta remains because of compatibility. So 1 by A2 will come into here, instead of A1 Q1, A2 Q2 will come, minus A12 is same, instead of Q2 Q1 will come. So these are the two compatibility equations in terms of that small A1, A2, A12 and Q1, Q2 and capital A1, A2. So this, if you remember these two equations, then by substituting the values, you can see here in the first one, 1 divided by A1 is 680. I am reading centimeters only, retaining centimeters only. 1 by 680 into small A1 is 1483 into Q1 minus small A12 is 366 into Q2. If you simplify this, you will get 2.189 Q1 minus 0.54 Q2. You can solve that as equation 2. Next, go to second cell, apply the similar type of equation. A2 is 2000 here, 1 by A2 is given as 2000, 1 by 2000 into A2, small A2 is 2409 into Q2 minus A12 is 366 into Q1. If you simplify once again this, you will get 1.2 Q2 minus 0.18 Q1. So that you can call it as equation 3. Now if you observe this second equation, third equation, LHS is same. In both the equations, LHS is same. Therefore, we can equate the RHS. So equating RHS of 2 and 3, and if you simplify that, you get the relationship between Q1 and Q2. So if you simplify that, that means 2.189 Q1 minus 0.54 Q2 is equal to 1.2 Q2 minus 0.18 Q1 if you do, and if you rearrange the terms, you will get Q2 as 1.36 times Q1. Now, we have got two equations now. So 4 is one equation, first is another equation. Now what you can do here is, you can substitute for Q2 as 1.36 Q1 in equation 1. Substituting for Q2 from 4 in equation 1, and if you solve, so the two equations will be reduced to one equation. If you solve that, you get the value of Q1 as 147 Newton. And Q2, after getting Q1, you can substitute that value here. 1.36 into Q1, that is 1.36 into 147 will give the value 200 Newton. So Q1 you have got 147 Newton, Q2 you have got 200 Newton. Now, what is the shear flow in the back portion, in the middle portion? That you can take the difference. So Q1 minus Q2 you can take. Of course, here you are getting minus sign means no problem. Minus sign means your assumed direction is wrong. It flows in the opposite direction. That means finally what you can say here is the shear flow directions. It is slightly, it differs here for the back portion. So I can show the shear flow direction like this. So Q1 is positive, so assumed direction is okay. Q2 is also positive, assumed direction is okay. It flows like this. Whereas Q3 it is negative, that means it flows like this. So Q3 will be like this. So this is what the shear, only he has asked for shear flow. So you cannot calculate theta because he has not given the value of G. Suppose if he gives the value of G, rigidity modulus as 40 GPa or 50 GPa or 80 GPa, something like that, then you can calculate angle of twist also. So then theta will be, either you can use this formula or this formula to calculate theta. So theta will be 1 by 2g A1 into A1 Q1 minus A12 Q2. So since you know the values of Q1 and Q2, you can substitute here Q1 and Q2 as well as G value, and if you simplify, you will get the value of angle of twist theta in radian per millimeter. Either you can use equation 2 or equation 3 to find theta. Here, he has not asked that, but anyway, I can write if G is given, that is rigidity modulus is given, theta can be found out either by using equation 2 or you can use equation 3. So that gives the angle of twist per millimeter. So this is the thing here is, since he has given different thicknesses, I have used this approach. If they give uniform thickness, we can do the problem like what I have done in the last problem, in the last video, whatever I have done, like that you can do. Since he has given different thicknesses, better to go like this. You have to calculate these closed integrals, and then you have to use the compatibility equation along with the torsion equation. You can solve for the shear flow. If they ask shear stress in this problem, you know the relationship between shear flow and shear stress, that is Q is equal to tau into T. So this equation you can use. Therefore, tau will be Q divided by T. So if you are calculating shear stress in the first cell, that is tau 1. If you are calculating tau 1, then you have to use Q1 divided by that whatever thickness is. The thickness is of course 0.06 there. So tau 1 will be Q1 divided by T. That is T1 you can say, that is 0.06. That value is your shear stress there. Tau 2 if you want, that is Q2 divided by this thickness. Of course, once again, thickness varies here. So for this segment, your total is different. For this segment total is different. For this segment total is different because they have different thicknesses. But Q2 remains same. Please note the point here. Q value remains same. Tau value may vary because this T may vary. So this is how you can, and for once again for tau 3 you can calculate it as Q3 by T. Q3, of course, you know the value there, 53 divided by this value, that is T value 0.09 centimeter. So you are going to get the answer in Newton per centimeter. Sorry, this is Newton per centimeter. You can write it as Newton per centimeter because it is shear flow. It is expressed as Newton per centimeter in this form. So this is how we can solve when different thicknesses are given and the shape is like airfoil shape, not a regular shape.